So what we did last time was for our ruled surface, okay, where we had the curve over here, C, we had the ruled surface on the right and left, we worked out what the derivative of the ruling is along the curve. Okay, we also expressed the ruling in terms of what the curve's triad is. Namely, we expressed R in terms of the component on T, the component on N, and the component on B. We worked out how it would change, and this was true just for any R vector being transported along a particular curve. And then when we did that, we identified these P's and Q's just from the calculation, and later on, and then I sort of observed that P's and Q's are orthogonal to R and orthogonal to themselves. So they also make another triad that is different from T, B, and N. So you now have two sets of triads, one that's associated with a curve, which is T, B, and N, one which is associated with a surface, which is R, Q, and P. And I then went on last time and proved to you basically that P and Q are very important to the surface. In fact, they are the vectors that if you look just at the surface, the geometry of the surface identifies it. In particular, I showed to you that Q and R, in other words, R lying along these lines and Q lying orthogonal to it, are in fact the principal vectors in your surface. Okay, so they are the vectors that you just, if you were to have any random piece of paper and you were to curve it, okay, you were to work out the metric in any coordinate system and the curvature tensor in any coordinate system, you solve that eigenvalue problem, and then you would have vectors that point, one along the ruling direction and two at 90 degrees to the ruling direction where the optimum curve is taking place. So the P's and the Q is the other principal direction, and the first one that corresponds to zero curvature is R. Okay, so R is the one that corresponds to zero in curvature, just straight lines, it's flat. Q is the one that corresponds to the curve that you've put into the paper. In other words, the Q direction points along this curve. It's always at 90 degrees to P because we guaranteed that, and that follows from the fact that our eigenvalue problem is dealing with symmetric matrices in 3 dimensions. And so there's a very, very distinctive connection between the Q and R and the surface. They lie tangent to the surface. And in fact, P is the normal to the surface, and that we also showed. Okay. So we effectively have two triads, one to the curve, one to the surface, and we're now going to start looking at the interactions between the two of them. Okay, and what I'm going to do now is simply, given a particular surface on the one side and a curve, I'm going to try and get you the conditions of how the curve connects them, okay, and how you actually work out what this other surface does. So one very important thing, look when I bend this piece of paper that has basically a half circle made on it, right? Part of this curve is due to the curve inside the piece of paper, okay? And another part, when I've bent it, of the 3-dimensional curve is a curve due to the bending. You see that, okay? If I have it flat, this curve is the curve inside the paper, okay? It's the curve basically written down on the paper itself. And then when I go and I bend it, the total curvature of the space curve changes, right? It becomes smaller. No, the curvature, sorry, becomes bigger. The radius of curvature becomes smaller. And it's always going to be, the curvature is always going to be bigger than the curvature it was when it was flat. Okay? So how do you see it? Just look at this curve. So you have the circle over here. Okay, it has a certain radius, let's say the size of my dinner plate. Okay, so the circle has a certain radius the size of my dinner plate. So it has a curvature that is 1 over the radius. Now I take this paper and I bend it, okay, and basically this curvature over here, the radius of this circle has become smaller, and therefore the curvature has become larger, and so that curvature will always be bigger than the curvature of the flat circle. Okay, and so what I'm going to do now is I'm going to separate out the curvature that is due to the stuff that's on the flat plane and the curvature that is due to the fact that I have bent the piece of paper. Okay, and because what is true is that when you bend this piece of paper, the curvature of the circle is the same for both this paper and for the other paper. But the curvature due to the bending of the page is not. That changes. Okay, so there's two components to your curvature. So let's see how we go and do that. And that actually, writing down those conditions gives us the conditions to write down the generator for the other surface. And I'm actually going to do that for this particular example. Okay, so we now have our two triads. The one for the curve, T, N, and B. The one for the surface, P, Q, and R. And what we want to do is express the tangent, okay, that's part of the curve, in terms of the triad on the surface. The triad fixed to the surface, that we can break up the components of the curvature that lies in the plane and the curvature that is due to the fact of you bending the paper. Okay, so the tangent to the curve lies in the tangent plane of the developable surface. Okay, that's just saying the tangent lies in the surface. And that plane we can span by the principal vectors P of the surface, namely Q and R. Okay, and I'm just going to shorten principal vectors by PV. So the way we do that is we now want to decompose T into the components of the principal vectors. So a component of T is going to point in the one direction that curves strongly, and another component is going to point in the ruling direction. Okay, and so the way we do that is simply to take T and to dot it in with R hat, and then to take T and dot it in with Q hat, and look at the components. So let's just, can you write T down for me? Or can you write the expression for R hat down for me on the board that we're going to use it? Okay, so that's just cos T plus sine T, or sine theta bracket, and we need another pen. Right, n cos phi and b sine phi. Okay, and can you just put Q and P up there as well? Okay, so P is just minus sine phi n, and plus cos phi b. Okay, and Q is just cos theta times in cos phi, the same bracket you've got in R, in cos phi plus b sine phi. Okay, and then minus sine theta t. Okay, so, right, so that is the relationship of P, R, P, Q in terms of T, N, and B. And what we now want is the inverse relationship, namely we want T's components on the principal vectors. And so the way we do that is, because R, P, and Q is an orthonormal triad, you can simply say T is equals to T dot R times r plus t dot q times q plus t dot p times p. Okay, and so if you look at what t dot r is, it's just cos theta. T dot q is just minus sine theta, okay, and t dot p is 0, right, because p is normal to the surface. So we've now got an expression for t in terms of q and r, and what we're also going to do, just because it comes up, is I'm once again going to identify u, which is orthogonal to t, but that also lies inside the plane. Okay, so t lies inside the surface, and another vector that also lies inside the surface that is orthogonal to t is just u. Okay, and you can just check that t dot u is equals to 0. Okay, so now what I want to work out, we know that t prime is equals to kappa n. That's just the Serre formula from the David, if you want to concentrate here, it's better for you. It's just the Serre formula from the Serre formulas. And then what we're going to do is we're going to now express n, okay, in terms of cos phi u minus sine phi p hat.
How do we get that?
There are two ways. The first way is you just take t prime, okay, you work t prime out the way we've worked out the primes of all the other things. In other words, t prime is then just cos prime times r hat prime minus, sorry, cos prime times r hat plus cos times r prime, okay, and you know what r prime is, minus sine theta prime q plus q plus minus sine theta q prime, okay, and you know what q prime and r prime is, and then you just substitute it in. Or in fact, you can go and you can express n in terms of p, q, and the other, basically do the same thing what I did with n, right? You could say n is express it in terms of r, q, and p simply by taking the dot product. So if you take the dot product of n with p, right, then you see you get minus sine phi.
So the dot product between p and?
So just as we express t,
Yeah.
okay, you can do the same thing for n. So you can say n is equals to n dot r times r plus n dot q times q plus n dot p times p. Okay, and if you do that, then you're going to get an expression in terms of p, q, and r, and it's going to turn out that it's going to be cos phi u minus sine phi p. Okay, so it's just projecting n onto this thing. That's one way. You can also just differentiate this guy and get that as well. And so what this does, it takes the derivative of t that's associated with our curvature, and it splits it into two components. Okay, so here the one component is kappa times cos phi multiplied by u, and remember u lies in this plane, plus a component that's normal to the plane that lies in the p direction. Okay, and so what I'm going to say now is that this kappa cos phi is exactly this curve's curvature, because it lies in the plane. Okay, so we've literally gone and projected the way our tangent vector changes in a manner that you have a component that lies in the plane that's entirely constrained by the fact that you have a curve in the plane, because the tangent vector's component in the plane will still always be tangent to this curve. And another component that lies normal to the plane itself. Okay, and this component over here is just the curvature of the curve that you actually drew on the plane. Okay, so the curvature of C projected onto the developable surface is, they call it kappa G in the Duncan and Dunker paper. That's why I use the notation. That's kappa G. It simply equals to kappa, the curvature of the space curve, times cos phi. Okay, and that curve is basically equals to the curvature of the unfolded crease CS, namely the crease that you actually drew on your page. Okay.
So kappa G is the curve, the flat curve curvature.
Yeah.
And just kappa is the curvature for the 3D curve.
For the 3D curve. Okay. And so what you've done now is so for example, when this page is flat, right? Then you have that phi is equals to 0. And then you have that kappa is just equals to the curvature of the curve. And when you have cos of phi taking on a specific angle, then the curvature is still, you have a component of the curvature that's in the curve, and then you have another component that comes to the paper bending. Okay, Duncan and Duncan calls this, the reason why they call it kappa G is they call it the geodesic curvature, the curvature collected onto this page. I don't like the name because I'm going to use geodesics for another thing. Okay, so I didn't call it that, I just say it's the curvature of the unfolded crease. Okay, so that's the one component. The other component is this kappa P, okay, and that's just minus kappa sine phi, and that's the curvature due to the fact that you've bent the paper, or the curvature due to the embedding. Okay, so in other words, the fact that you've taken this page and you've made a cylinder out of it is the curvature that gives rise to that second curvature. And that you now have an additional condition. We know that the square of these two, okay, is restricted by the fact that kappa P squared plus kappa G squared must be equals to kappa. Okay, and this is wonderfully restrictive. Okay, so what does that mean? Right? The space curve has a curvature that's common to both sheets. Okay, and that curvature is kappa. Okay, so that fixes that curvature. This curvature kappa G, which is the curvature of the unfolded crease, that thing is also the same. It's the same flat crease, whether you fold it or not. Okay, so for both sheets of paper, this side and that side, you have the same big kappa, you have the same kappa G. So that immediately implies that this kappa, due to being projected, okay, has got to have the same magnitude, definitely. The only way it can differ between the two sheets is in sign. Okay. The one will be positive and the other will be negative. And so you can see this over here. In some sense, if you look at the sheet, right, this inner one is curved hollow, okay, so positive, and the other one is curved convex. So that's how the two are joined. It's simply the normal curvature, in some sense, the curvature projected normal to the sheets that changes sign. So very, very restrictive in choosing the curvature. Okay, so when you join two developable surfaces at a space curve, kappa G and kappa are the same for both sheets. Okay, while kappa P, and this is how I indicate the left and the right sheet, have the same magnitude but differ by a sign. Okay, and you have another thing, okay, that, remember we worked out those eigenvectors for the principal curvature. The one was 0, and the other one on the surface itself, I said was lambda p, which was simply equals to, it was proved on the previous slide, but it's basically, when u 0, it's simply kappa sine phi over minus sine squared theta. So that's the principal curvature of the sheet itself. So for example, suppose you bend this guy into a cylinder with a radius rho, then lambda is just 1 over rho. Okay. So that curvature is then simply related to the normal curvature simply by this formula, because I've replaced minus kappa sine phi with kappa p, just its definition. Okay, and this formula is just going to be useful, especially for the coming example, because I'm going to bend it into a cylinder.
Can I just ask, so basically when we solve for kappa, we can get on, for instance, the left-hand side, it has a positive sign, and on the right-hand side, it has a negative sign.
Yes, kappa p.
Kappa p,
yeah.
Yes. So, but in the definition of kappa p, we say it's minus k sine phi.
Yeah.
Can't we just then say that is a plus or minus sign?
Yes, you
So
will.
it doesn't matter if we use a minus or not. Depending now, if we restrict it to one side, I get we say it's minus, and then maybe the side is the negative side, so then it cancels out. But in the general formula, does it then matter if we have the minus or not?
You have to be careful, because the sides make a differ. The signs differ. Just another comment, the fact that you switch the signs over here, look at what phi is. Look at what sine phi does. If you look at r hat, you have cos theta times t plus sine theta, and sine phi is the angle the thing makes with b, which is your binormal vector. Okay? And remember, right in the start, or when I started talking about this stuff, I said there's that very fancy theorem that the two sheets, the binormal vector, bisects the angle between the two sheets. And that is exactly what we've just proved. Okay, so if the sine phi is plus for the one sheet, minus for the other sheet. So you literally have your binormal vector, say, for example, sitting vertically. The one sheet has a phi angle that does that, and the other sheet has a phi angle that's just minus. That's exactly the same. So we have effectively proved, in some sense, with a statement that they have different signs, that the binormal vector bisects it.
But is this what you mean? So it does not matter if you say plus or minus, you can just say plus or minus. Is that what you mean?
Yeah, so in the general case, plus or minus, but if we're focusing on a side, then we should know whether this is the
positive or the negative side. Yeah, okay. Yeah. So I was careful when I did this, because I've never done it before, and so then I try and be as strict and as rigorous as possible before I start making generalizations like that. Typically, I tend to write things out, and then only afterwards, when I'm super sure and I have a few checks, then I go and make your generalizations. Otherwise, I've experienced that I get myself into trouble. Okay, and I don't like trouble that I can avoid. Okay, and then just when you go, if you guys go ever and read the Duncan and Duncan paper, here is the relationship between my angles and his angles. Okay, so just as a legend, the pictures in the Duncan and Duncan paper are very useful. Okay, they give you another idea of how to think about it. As I said, I initially, when I read it the first time, I had no idea where he got the stuff from, and that's why I started working it out this way. But by all means, some people's minds think... There's certain things you can learn from certain people, because I have this theory that some people's minds think differently in different ways, and there's certain teachers you learn things from, and there's certain teachers that you learn other things from. So the fact that I didn't initially understand him doesn't mean that you won't, okay? But his pictures are exceedingly useful. So definitely go and look there. Okay, so now let's just use that information we've gotten to see how far we can go with our circular crease pattern and see what else we have to fix. Okay, because so far all I've told you is that basically the normal vector B bisects the two surfaces. Let's see what that means and see how we actually do the calculation. Because what is interesting is that there are very few practical calculations with this type of stuff. Okay, and in fact, I've not seen the calculation I've given you anywhere, so I'm not going to give you a reference. It's here. But the way I describe it might be useful, because eventually I want to describe more complicated things. So I wanted a simple example to work with, and that also goes and illustrates these ideas. Okay, so what we're going to do is we're going to look at a half circular crease pattern. So that I write down the crease pattern in 2 dimensions. It's simply cos S sine S. Okay, so there we have it. And what you have to do in addition is you have to decide on a ruling on one of the sides. So I'm going to have S is my parameter. It goes from 0 to 2 pi and from 0 to minus 2 pi. Okay. The ruling I'm going to say, I'm going to put the ruling on the left. For the problem set, you guys are going to get a ruling on the right. Okay, so that you can do a similar problem on your own.
So if we're doing ruling on the right, it's the arrows is going to go the other side.
The arrows is going to go the other side.
Yeah.
Okay. And I'll specify what it is, because you need to specify the ruling at least on one side to actually solve the problem. So I have a ruling on the left. Okay. And just more arrows. So that's a unit vector. S is my parameter. It's already arc length parameterized. So this is what makes this example nice. The example I'm trying to do with a flasher, I have no way of getting it arc length parameterized, which makes it a lot harder. So anyway, this is arc length parameterized. There's our ruling. Okay, now we can start identifying already what our tangent vector to the curve dotted in with a ruling is. Okay, just in the plane, but that's true, that statement is only true in the plane. So what we do is we basically work out t, which is just the derivative of cs, and we dot it in with rl, okay, and then we get that the ruling is sine phi. Oh, sorry, this thing is equals to sine phi, sine s, okay, and that immediately gives us, okay, because we can express this rl in general in that way, that sine s is equals to cos of theta. Okay, you see what I'm doing? I've got a prescription for my curve, I've got a prescription for the ruling, but now I want to go and work this machinery out, use that machinery, and so I know that theta is a function of s, and so I've already got what theta is as a function of s.
Sorry, the ruling is basically our R vector.
The ruling is our R vector projected onto the surface. So yeah, it is our R vector. Okay, so all I'm specifying now is that the ruling, I'm specifying the angle between the curve projected onto the surface and the rule lines that I have. Okay, so like this, I have my ruling that's drawn relative to the curve, and that ruling remains the same, and the angle between the ruling and the tangent vector remains the same even when I distort the page itself. Okay, so that's why I can fix theta equals to pi over 2 minus s. So I have theta as a function of s. Okay, now what I'm going to do is I'm simply the curvature in the developable surface itself. In other words, the curvature of this curve is just 1, okay, because it's a circle of radius 1. So there's my kappa g for this particular curve. Okay.
So we can work out kappa.
We can't,
You still need kappa b.
Yeah, but we have a kappa g is kappa cos phi. Okay, but we don't have a phi.
You don't have a phi yet.
Yeah,
Okay. All I know is that, so this is the power of the curvature of the unfold crease. This kappa g you can get just from the flat picture. Okay, so what I'm doing now is I'm basically extracting all the information I can extract just from my flat crease curve. Okay, and so the one thing it gives me is theta, which is the angle between the ruling and the curve. The second thing I get is the geodesic curvature or the curvature of the unfolded crease, and that's my kappa g. Okay. And what that immediately tells us is that the curvature of the space curve must always be bigger than or equals to 1, okay, because of this definition that kappa g is simply kappa cos phi, and cos phi is always less than or equals to 1. Okay, so we have a condition on our kappa. Okay, now what we're going to do is I'm going to bend the sheet on the left where I've defined the ruling into a cylinder with radius rho. Okay, so I'm literally going to take that sheet. I'm going to do this to it, and I'm going to have my cylinder. It can either be, if rho is small, I can bend it up tightly. If rho is bigger, I can bend it flat. Okay, so rho I'm going to leave in as a parameter for my surface. Okay, so this is radius rho. And so what that's going to do is my principal curvature, okay, that's at 90 degrees to the ruling. In other words, my Q vector, that in this case my ruling lies in the x direction, and my principal curvature is guaranteed always to be at 90 degrees to x. Okay, that lies in the y direction. So what I'm literally going to do is I'm going to take a line like this and bend it into a cylinder. Okay, so that's what the action of making the cylinder is. And in fact, let's just do all the others. So I'm literally going to take these lines that are at 90 degrees to my ruling and bend them into a cylinder. And that cylinder's radius is going to be rho. And that means that the principal curvature of the cylinder itself, of the surface that I make, is going to be 1 over rho. Okay, so this principal curvature, this lambda p that I get from my eigenvalue problem, has to do only with the surface. Okay, and that is the curvature of the cylinder I'm bending in. Okay, so I have lambda p now. Okay, and so what that then gives me from this formula over here is that kappa p is simply equals to sine squared theta over rho. Okay, so that is the curvature projected in the normal direction, normal to the plane. So I have kappa p already. And so what's basically going to happen is this long solid line over here, okay, I want to identify it with my parameter on the surface. Okay, and the way I identify it with a parameter on the surface is basically along the solid line, the only coordinate is y. Okay, and so I can either say I've gone y distance along this curve, or I can say I've traversed this y distance along the line, or I can say I've traversed this curve a distance s till I get to that same y value. Okay, and then I get that this y value over there is simply sine s. Okay, you see that, right? Because S, this is a unit circle, S is basically that angle, right, between the origin and that point. And so the height there is simply sine S. Okay, so the y coordinate along this line, I put, I know that it's equals to sine S if I want to relate it to the parameter on the surface. The reason I'm doing that is I ultimately want to get an expression for my crease that I've bent up.
Oh, so the sine S is just because of the surface is defined as cosine sine. Okay,
yeah. Okay, that's it. That's it.
I was like, why sine and not cos?
No, that. Okay, so that's the y component of the crease. Okay, so. Okay, so I'm basically going to distort this line into a circle, okay? And the circle, and this is the mistake you guys have been making with your oscillating circles. Have a look at where you put the center, okay? The circle, but I'll put the memo out on the internet as well, on the internet as well, so take a look at it. The circle has its center point above the flat plane. So the circle, when I can view this thing as this thing lies flat, then I bend the thing up like that, and I bend this other thing up like that, and then my circle center sits over here, okay, a distance of the radius above the place where I'm bending it. So the z value of the circle is z minus rho. It's the center is at z equals to rho, 0, 0. Okay, and it's just going to be this curve that I'm bending, so plus y squared equals to rho. So that's literally a circle sitting, a cylinder sitting over here that I bend the page onto. In fact, I can get a demo. Okay, so there's my cylinder with a radius. The center point is in the middle, and so I'm going to bend the page around it. Okay, and so if I want a parametric expression for the new thing that I've curved it onto, it's basically 0, okay, because I'm just keeping x equals to 0, and then it is rho sine y, rho times 1 minus cos of y. Okay. Do you get this one? You see why I do that? Not obvious. Okay, so let's look at this. We have this circle. We have this parameter s going along it. Okay, what happens now is that y plays the role as the parameter s. Okay, right, so we've gone a little distance y along the big curve we've curved up. Okay, and we want to turn this thing into an angle. Okay, so y divided by rho will give you the angle you've traversed when you're bending the curve upwards. Okay, so y over rho is the angle that you go when you bend, actually take this flat line and you bend it up. Okay, and y is just sine of s. Okay, so it's basically the angle, little bit of angle that I've bent this curve upwards multiplied by rho. This is the y component. The z component, here's the origin, which sits at z equals to rho, minus the little part of the circle, which is the other component, the angle cos sine s of rho, the little angle that you've bent it upwards. Okay, so that's a way to parameterize this curve using s. And you can, if you go and you actually plot this curve, you'll see that it does exactly what I say it's going to do. Okay.
So that equation, you can't, or you can, but I'm not sure how, to get it analytically, because we basically just looked at what y is.
Yeah.
And then try to see, okay, so you will go up with it a little bit of an angle, so it's going to be that sine s rho, but there's no really way to plug in things to get that.
That's insight. I mean, it's basically that's insight. It's basically if you take a flat, it's setting up a nice problem I can analytically solve. But I mean, basically, if you take a flat piece of string and you say you want to bend it round into a circle. Okay, that's how you would do it.
Yeah.
Okay. And it's not in some sense a guess, it's the only way you can write it down actually.
Yeah, but very harder problems will get harder to visualize, so it's harder to parameterize it.
Yes, and that's the reason why these examples don't exist.
Okay.
Okay, right. I don't think you'll find this easily in a textbook anywhere. Okay. And that's why I want to have a go at the problem, because some of these things, there are nice examples. Okay. So this is now the curve I bend it into, and I'll actually plot these things for you on the next slide so you can see what happens, because I had fun. Okay, so what we now have is that this thing distorts into a circle, and this crease CS also distorts. And it's very easy to see how it distorts, because we already know that if this cylinder this thing distorts into a circle, then those things are on the same circle. Okay, so this points over there's y and z coordinates will just be the same as this, because you've literally taken the page and distorted it up. And so the crease then distorts into this parametric equation. Okay, so it's just cos of S, because that's the x coordinate of the crease, and then it's y coordinates, because we managed to parameterize this distorted version of the curve using sine of S, okay, which was simply equals to its y component. It's very easy to write down the distortion of the crease as well. One thing to check is that the arc length parameter along the crease has to remain the arc length parameter of the distorted crease. Okay, so what you have to do is work out the tangent to this thing. It's just a check. The construction should have kept it that way, but it's a check. You work out the tangent of C, okay, just by taking the derivative, and then you get this expression. And if you dot this in with itself, what you get is sine squared plus cos squared times cos squared plus sine squared, which is 1. So you get sine squared S plus cos squared S. Okay, so it is still arc length parameterized, which is nice. So we have now a very nice construction. We have this 3-dimensional space curve. We have its 2-dimensional crease pattern. We have the geodesic curvature due to the crease pattern. We already have how theta is related to S. Okay, and then we have our external geometry of our cylinder being fixed by a constant rho. So it's a very nice toy problem to actually work with. So, okay, so what I'm now going to do now, I'm just going to take this picture, I'm going to flip it because I need my 3rd dimension for plotting purposes. And I'm going to put it over there. Okay. And what I'm going to do, so this is all the other stuff that we've had over there. I simply want to go and I want to plot it, okay? So this distorted crease curve is I'm basically going to take this thing and bend it upwards, and I'm going to bend just from pi over 2, minus pi over 2 to pi over 2. Okay, so there it is. So as you bend it upwards, this length of curve, that is exactly this parameterized curve that I've plotted, where S goes from minus pi over 2 to pi over 2. Okay. Now, the next thing is I'm just going to distort all the other curves, because every single curve in my principal direction, I'm simply going to distort into the cylinder, and there we go. And then the final thing is I actually want to plot that thing I derived, and it fits beautifully. Okay. So I'm going to stop there because I think somebody's got to go and teach. But just to show you that I've now got my space curve parameterized, I've got my ruling, and we can start working out those conditions and see what it actually means in our final lecture on paper. Okay, right. And I'll get you the notes up as well as the next problem set that you can give it a go.